and he has joined Microsoft. He's a senior researcher at Microsoft. But I think there are probably some very interesting collaboration opportunities that can arise now that he is actually in the neighborhood. Not that it matters in this COVID world, but it just still somehow feels like, maybe, hopping across the lake or something and grabbing a cup of coffee with Deepak would be kind of a possibility. But anyway, so he's worked on Pipe Dream and a bunch of other papers. The Pipe Dream is one of my favorite papers. I've read it a bunch of times. I still don't quite understand pipeline parallelism all that well. So, but there's some very interesting performance trade-offs. Just reading the paper from the perspective of being able to understand what those trade-offs are is super interesting. So I presume that he's actually going to talk a little bit about that as well as part of this talk. So let me let Deepak then go ahead and tell us all about what he's been doing in the past few years.
Well, yeah, thanks a lot for the kind introduction, Arvind. Really excited to be here. So yeah, today I'm going to be talking about work that I did primarily at Stanford, but also in part at internships at Microsoft Research and Nvidia. And this is joint work with a number of awesome collaborators across Stanford, Microsoft Research, and Nvidia. So deep learning has helped generate state-of-the-art results across a really broad range of applications. These include machine translation, speech-to-text, game playing, and even newer classes of applications like drug discovery and writing code. However, training and inference of modern models is extremely computationally expensive. This is a graph from the recent GPT-3 paper that shows the number of compute operations needed to train various natural language processing models. The largest GPT-3 model here requires about 8 petaflop per second years of computation, and even more recent models require more computation to train. And so as Moore's law slows down, we're seeing a wide variety of parallel hardware, such as GPUs, TPUs, multi-core CPUs, and even other domain-specific accelerators to meet this massive need. Each of these hardware architectures have different programming models and show heterogeneous performance behavior on the wide plethora of deep learning models that we're commonly using today. And I think it's not a stretch to say that this heterogeneity is only bound to increase in the coming years. This heterogeneity also complicates traditional deep learning workflows. So typically you have some expensive heterogeneous accelerators that are part of a shared resource pool. Schedulers then will grant resources to different users based on their demands. And now, given dedicated resources, users can use a runtime or framework like PyTorch or TensorFlow in order to execute their training or inference tasks. For modern deep models, computations are iterative, long-running, and quite compute intensive. The goal of most users in this whole process is to train and deploy their models with as high performance as possible. However, in practice, users are often forced to make a number of key decisions that critically impact performance. For example, it's not always clear how users should pick specific resource types for their jobs. For example, even if one was to constrain themselves to Nvidia GPUs, it's not clear whether one should use a V100 or a A100 GPU. A sensible policy could be to just use the fastest GPU type available, which is the A100 in this particular case. But this could lead to unintended consequences, such as jobs being stuck in queues, waiting for resources all the time, especially if every user goes through the same decision-making process. Users do not really need to think about this question when just using the same type of device. And then even once one is given resources, users need to decide how to train their model or perform inference. Particularly with training, this process can take days to weeks, meaning users might want to parallelize their computation to get results back in reasonable timeframes. Should the user use the same one-size-fits-all parallelization strategy for all models and resource configurations? It's not completely clear. And so what happens in practice is this is all extremely complicated for users. Users end up making suboptimal decisions. And consequently, we can waste time and dollars. And so in this talk, I try to make the case for how intelligently reasoning about heterogeneity in terms of models, hardware, and even objectives is essential in achieving really good performance for machine learning training. And I will show that doing this allows us to obtain throughputs of up to 502 petaflops per second when training a model on thousands of GPUs. And it can also help us improve average job completion time for a collection of jobs by up to 3.5x using the exact same set of resources. And so consequently, users are able to use their resources much more efficiently. So I'm going to discuss how this principle applies in two broad contexts. First, I'm going to talk about distributed training, where we're given a fixed budget of resources, and we want to train a model as fast as possible using these resources. So training a deep neural network model at a really high level involves finding some weight parameters W that fit a training data set, usually consisting of inputs and maybe associated labels. A forward pass through the model generates intermediate activations as well as some prediction. This prediction could be incorrect. And so errors between the prediction and the true label are backpropagated through the model in a backward pass. This whole process generates weight gradients that can then be used to update the model's parameters. It's important to note here that this backward pass uses both the weight parameters and the intermediate activations as inputs in order to compute these weight gradients. Optimization is typically performed in iterations, and each iteration can be parallelized within an accelerator, but also across accelerators. And so our goal here is to provide heterogeneity-aware distributed training. And really, when I say heterogeneity-aware, I mean heterogeneity along two different dimensions. The types of models that we're trying to train are quite heterogeneous. There are different types of models for different application domains, but there's also heterogeneity along the hardware dimension. And so two examples here of this type of heterogeneity that I'm alluding to could be, the first example is we're trying to train models with a really large number of weight parameters with particular architectures and operators. And the second example could be maybe we also want to achieve efficient training on hardware deployments where we have really slow interconnects between different servers. And so what I quickly want to note here is that a single parallelization strategy cannot possibly do well across all of these different scenarios. And so there are a couple of existing distributed training paradigms that people have commonly used today in a variety of different settings. So the most commonly used method for distributed training is what is known as data parallelism, where every device has a copy of the model, the input data set is sharded, and weight updates are exchanged periodically between each of these different devices. Another method of parallel model training is model parallelism, where a single copy of the model parameters are split over multiple devices. It turns out that this can be performed in a couple of different ways. For example, each layer or operator in the model can be partitioned over multiple devices. This is commonly called tensor model parallelism. Alternatively, layers can be striped across multiple devices. A single batch of samples on which we do optimization can be split into smaller micro batches, and then execution can be pipelined across these micro batches. An interesting thing here to note is that each of these approaches has trade-offs along a number of different axes, such as amount of communication. To drill into this point a bit deeper, let's consider these different forms of parallelism. So with data parallelism, we're actually performing all reductions of weight gradients after every iteration in our optimization procedure. It turns out that these all reductions can be quite expensive for large models, simply because you're doing a collective communication operative, and the number of parameters in the model can often be quite large. With tensor model parallelism, we're splitting individual layers or operators in the model over multiple accelerators. Depending on the exact semantics of the operators that are being split, different communication patterns are needed. So for example, Megatron proposes a particular splitting strategy for transformer models that are commonly used in NLP applications. These transformer blocks are somewhat complicated, but they do consist of a couple of different matrix multiplications. And when using tensor parallelism, we are essentially splitting these matrix multiplications over these multiple GPUs and performing, in a sense, distributed matrix multiplication. But it turns out that specific matrices are split in a row-wise fashion, and other matrices are split in a column-wise fashion. And Megatron really designed a custom strategy based on how these different operators are composed in the transformer block. And it turns out that this all reduction that you need to perform both in the forward and the backward pass as a part of doing these distributed matrix multiplications can be quite slow across inter-server communication links. So usually the way GPUs are laid out in data centers, you usually have multiple GPUs on the same server, and the bandwidth that's available between GPUs on the same server is quite high. In practice, Nvidia has this proprietary link technology called NVLink that supplies high bandwidth between GPUs on the same server. But bandwidth across servers is quite a bit lower. And so usually tensor model parallelism scales quite well within a server, but scales less well across servers. And so finally, with pipeline parallelism, layers or operators in the model are going to be sharded over multiple devices. In other words, each device is responsible for a subset of the layers or operators in the model. We then split a larger batch into smaller micro batches and pipeline execution across these micro batches. We can think about this procedure visually. So here I've taken a model and split it over 4 devices. And one thing to note here is that when I perform this interlayer model parallelism, I have this sequential dependency across devices. And so a single input needs to pass through the 4 devices first in the forward direction in order to execute the forward pass. And then that same input needs to flow through the pipeline of devices in the backward direction in order to perform the backward pass, where we actually compute the weight gradients that are then used to update the model's parameters. And so one way one thing you can note here is that this procedure seems quite inefficient. There's a lot of idle time spent where devices just wait for other devices to perform the requisite computation. And so one way to kind of accelerate this whole process is to split batches into smaller micro batches and then pipeline execution across these micro batches. And so here we're taking this batch A and splitting it into 4 smaller micro batches, A1, A2, A3, and A4. And then I can pipeline execution across these 4 micro batches. And so now you can see that, and now what we do in this procedure is we step the optimizer and update weight parameters only once all micro batches in the batch are completed. So basically where my cursor here is now. And so one thing to quickly note here is that execution for this particular batch finishes much more quickly in this pipeline setup compared to the unpipelined setup. So in the top figure, execution doesn't even complete within these many timestamps that I've shown. But here you see in the pipeline setup in the picture at the bottom, you see that execution actually completes within these many timestamps. One thing I do want to note here is that pipelining still leads to some wasted compute cycles. You can see that every device is idle at the start and end of a batch. And we call this a pipeline flush, as devices wait for inputs to flow through the pipeline and then subsequently get drained out. We can also exactly quantify the size of this bubble. It's just equal to P-1 forward passes and P-1 backward passes, where P is the number of, is the pipeline parallel size, right? So in this particular example figure, P is equal to 4, right? And so we spend 3 forward passes at the beginning of a batch and 3 backward passes at the end of a batch, kind of waiting for inputs to flow through the pipeline and then drain out.
Hi, Deepak, I have a question.
Yeah, go ahead.
So say in device 4, after you perform the backward pass of A1, did you update the parameters immediately, or you end up, update the parameters after you propagate the gradient to device 1?
Yeah, you can start the parameter update for device 4 as soon as you're done with its backward pass. You could also just wait until device 1 is ready to update its parameters. It doesn't really matter. You can kind of move that optimizer step forward or backward, and it doesn't make too much of a difference. Yeah,
but this one is not equivalent to the figure in above, because it is, and the gradient is updated asynchronously, not synchronously. Is that right?
No, the gradient is updated synchronously. So basically B1 is only going to start after A4 completes and the optimizer is there. Yeah, go ahead.
If you update the parameters after, say, on device 4, if you update the parameters after the backward pass of A1, and the way you compute the
so that's a good point. So you don't update the parameters on device 4 after A1. You would update the parameters for device 4 after A4. So this is the idea of so essentially you step the optimizer only after all micro batches in a batch complete execution.
That makes a lot of sense. Thank you.
Yeah, good question. Any other questions?
I also have a question.
Yeah, go ahead.
So do you need to store other intermediate activations on each device? Like, for example, device 1, when you do the back pass for A1, you need to reuse that intermediate result, right? So you need to store other activations of A1 to A4.
Yeah, no, great question. So it turns out that you need to store intermediate activations for all in-flight microbatches. But you can basically garbage collect those intermediate activations as soon as you run the backward pass for the respective microbatch. So basically, as soon as I'm done with the backward pass for A1, I can garbage collect the intermediate activations for the microbatch A1. But actually, the total number of intermediate activations that you need to maintain state for is just going to be bounded by P, where P is the number of devices in the pipeline. So if I had a batch that consists of 8 microbatches, the maximum memory overhead for this particular schedule is still going to be 4 microbatches worth of intermediate activations. Yeah.
Okay. Thank you.
And we can talk about this point more offline too, if it doesn't make sense to you.
Okay.
Yeah, cool. Yeah, any other questions? Cool, awesome. And yeah, definitely feel free to just interrupt me at any point with questions as they arise. Okay, great. So those were different parallelization strategies that people use. And it turns out that each of them have existing trade-offs. And so given these trade-offs, it's often necessary to compose them in order to actually achieve high performance at scale. But it turns out that it's not actually easy to do in practice. So let's consider a simplified setting where we are just using tensor and pipeline model parallelism. So let's assume that the total number of GPUs that we have at our disposal is n. Let's assume that the number of GPUs that we use for tensor model parallelism is going to be t, and the number of GPUs that we use for pipeline model parallelism is p. And so we now have this added constraint that t times p is going to be equal to n. So now we can exactly quantify the pipeline bubble size, which you can think of as the fraction of ideal computation time where devices are idle. And so there's another parameter here called m, which is the number of micro batches in a batch. So in the example on the previous slide, m was equal to 4, right? A batch consisted of 4 micro batches. And so the pipeline bubble size is going to be p minus 1 times the time for the forward pass plus the time of the backward pass. Remember, I said that the pipeline bubble consists of p minus 1 forward passes and p minus 1 backward passes, divided by the ideal time you would spend in an iteration computing gradients for a particular batch. Now, since a batch consists of m micro batches, TF and TB are the forward and backward processing times for a single micro batch. So the total ideal time spent processing this particular batch is just going to be m times TF plus TB. So now we can do some simple arithmetic. TF plus TB cancel on both sides. We see that the pipeline bubble size is just going to be p minus 1 divided by m. But it also turns out that t times p is equal to n, right? So I can now express the pipeline bubble size in terms of the tensor model parallel size, right? And the number of GPUs that I'm going to be using. So one quick thing to note here is that as the tensor model parallel size increases, the pipeline bubble size is going to decrease. However, it turns out that as the tensor model parallel size increases beyond the number of GPUs in a server, we now are going to have to perform this expensive all-reduced communication across servers, and this is more expensive. And so we immediately see that increasing just this one parameter, which is the tensor model parallel size, produces two effects that are at odds with each other. So if we increase the tensor model parallel size, the pipeline bubble size decreases, and our compute devices spend less time idling, which is good for performance. But also, as we increase the tensor model parallel size, we also increase the amount of expensive communication that we need to perform across servers, and this is bad for performance. And so we can actually look at some empirical results that validate this kind of trade-off. So here I'm going to show an experiment for a 162 billion parameter GPT model. And I'm going to show training throughput using 64 A100 GPUs. On the y-axis, I'm going to show throughput per GPU, so higher is better. And on the x-axis, I'm showing a number of different configurations using those 64 GPUs. So 232 means I use a pipeline parallel size of 2 and a tensor parallel size of 32. And similarly, 32.2 means I'm using a pipeline parallel size of 32 and a tensor parallel size of 2. And so I'm showing results here for two different batch sizes. And we can kind of see that there's an interesting trend here. In particular, when the tensor parallel size is small, we see that throughput is low because we need to perform all reductions for tensor model parallelism across servers, which is expensive. But we also see that when the tensor parallel size is small, the pipeline bubble size becomes large, and that is bad for performance as well. And in this particular example, using 8 GPU, using servers with 8 100 GPUs each, we see that there's a happy middle ground at pipeline parallel size equal to 8 and tensor parallel size equal to 8, where we're able to keep the pipeline bubble reasonably small, but we're also able to keep the all reductions for tensor model parallelism within a single 8 GPU server. It turns out that there are even more trade-offs when I also add data parallelism into the mix. And so this question of how to even use existing forms of parallelism to train my large model at scale is quite complicated. It turns out that we can also change the pipeline schedule that we use. So for example, so this is the same pipeline schedule that I just showed you, where we're assigning different consecutive groups of operators or layers in the model to different devices. And so here you can see that we have 8 micro batches in a batch. But it turns out that we can actually assign multiple pipeline stages to a device. You can kind of think of this as using some sort of interleave schedule. And the nice thing about this interleave schedule is we can reduce the pipeline bubble size as indicated by this black line indicating the point of the pipeline flush moving forward in time. And so I don't want to spend the exact mechanics of what's going on in the bottom figure are not super important. But one thing I do want to say is that this smaller pipeline bubble that comes about from this new schedule in the bottom figure doesn't come for free. We're able to reduce the pipeline bubble size by increasing the amount of communication that we need to perform in the pipeline. And the reason why there's more communication here is basically because we need to pass through the same device multiple times. And so essentially the trade-off here for using this new pipeline schedule is that we have a smaller pipeline bubble, but we introduce more communication. And so we can actually see these results in practice as well. This is a 175 billion parameter GPT-3 model, 96 80GB A100 GPUs. And you can actually see that the optimal schedule is somewhat dependent on the batch size. You can see that there's actually a large gap between the interleave and the non-interleave schedules when the batch size is small and the number of micro batches in a batch is also small, but this gap really closes. And if I were to run this for even larger batch sizes, at some point the blue curve will overtake the orange curve. And so we can see that here that the optimal choice of pipeline schedule is also dependent on other problem parameters, such as the batch size that we are using.
So Deepak, just a couple of quick questions. So one was that I wanted to pick up on this batch size question as well. But before that, you mentioned that there's more communication. Is it more communication, or is it just that the communications become fine-grained and as a consequence more expensive?
No, it's that you're actually communicating the same size tensor more times. So here actually between any two device boundary, the size of the tensor is actually the same. Yeah, it's for these transformer models anyway. But what happens is you need to send that same size tensor more times, and that leads to more communication. You can essentially, like an easy way to think about this is there are more device to device communication boundaries in the bottom figure compared to the top figure, right? And that means more communication. Yeah.
So what's communicated across the device boundary is not activations, or is it?
It is activations, but essentially, like the computation for these transformer models is basically transformer blocks. And so in the top case, you can think of every blue box doing the forward pass for, let's say, 4 transformer blocks. In the bottom figure, we're doing the computation in every less wide box for 2 transformer blocks.
Interesting.
Right. And so the kind of data that's being communicated across devices is this intermediate activation between these blocks, but that's the same size in both cases.
So that's essentially what you're saying is that's independent of the batch size. Of the
right, exactly. Yeah.
Okay. And then the other question that I had in the next figure was really kind of what was the kind of the just from a GPU efficiency perspective.
Yeah.
What is kind of in this graph, where do you think is the kind of the sort of a good place in terms of micro batch size, being able to max out, I mean, get close to a reasonable GPU?
Yeah, so the other thing here is that batch size also affects convergence properties of the model. And so you don't, if we're just thinking of this from a systems perspective, from performance, you want to pick the largest batch size possible. This basically makes sure that you can amortize away these pipeline bubbles, and you can essentially ensure that your GPUs are well utilized most of the time. But yeah, in practice, there are other considerations too, right? So like some of these large models, you can't really push the batch size to infinity. You need to use like a batch size of like 2048, for example, right? And so here, I'm showing the batch size only for 96 GPUs. But in practice, people will augment this with data parallelism and train on like 2000 GPUs. Right. And so you can think of like the end-to-end batch size in those larger deployments as the batch size that I show on the x-axis times how many ever extra GPUs you're using for model parallelism, right? So like if I'm using 2000 GPUs, 2000 divided by 100 is 20, right? So multiply these batch sizes on the x-axis with 20 to get like the actual batch size you would get at the full scale.
Awesome.
But yeah, like from just the systems performance perspective, you probably want to use you could push this graph out along the x-axis and you could get even higher throughputs. I guess one other thing I want to point out here is that the peak throughput of these devices is like 312 teraflops. So here we're achieving about 50% of peak. But you can't actually reach 100% because you have a lot of like memory bound operators and so on. And so I would say that like we've been able to achieve throughputs of 170 teraflops per second, and that's really good. Yeah.
Got it. Okay, thank you.
Any other questions?
I have a quick question. Can you go to the previous slide?
Yeah, sure.
So so from device 1 to device 2, is the communication synchronous with the computation?
Yeah, so basically we're considered a simplified setting here where all the communication is synchronous. This includes communication between individual pipeline stages. Yeah.
Thank you.
Yeah, you could try to make some communication asynchronous, but it turns out that, to do computation on device 2, you need some input from device 1, right? And so essentially on the receive side, you still need to wait. But on the sender side, you could probably do that asynchronously, but that's not what our implementation did. Our implementation basically waited until the tensor was communicated to device 2. Yeah. Any other questions? Okay, great. So it turns out that there are actually many different factors at play that can affect the performance of distributed training at scale. This includes the degrees of parallelism, the pipelining schedule, also things like the global batch size and the micro batch size. And each of these different factors influence the amount of communication, the size of the pipeline bubble, the memory footprint, and so on. And actually determining how these different factors should be balanced is quite challenging. And our supercomputing paper from last year has some more details on how to kind of think about how these different factors should interact with each other. The upshot of all of this is that once we carefully navigate these various performance interactions, we're able to achieve quite strong scaling performance. This is a weak scaling setup where we increase the model size as we increase the number of GPUs. And we see that at really large scales, we're able to efficiently run training iterations for GPT models with up to 1 trillion parameters using 3,000 plus GPUs with performance of about 502 petaflops in aggregate. So takeaways from this part of the talk is that one parallelization strategy cannot possibly fit all models and all hardware deployments. Existing parallelization strategies have various trade-offs, and these need to be considered carefully in order to obtain good aggregate performance. But the end result is that if we are able to balance all of these factors correctly, we can achieve more cost-effective distributed training. And so now I'm going to switch tracks a bit to scheduling, where we want to assign resources from a central pool to jobs submitted by various users. Sorry. And so you can think of this resource allocation problem as a scheduler allocating resources from a central pool to different training jobs, usually while taking into account some objectives specified by a cluster operator. So this objective could be fairness, could also be something like cost and make span. And scheduling really is an extremely well-studied problem in computer systems in other contexts as well, for example, in big data clusters. One thing that's interesting about the machine learning domain is that we have a lot more hardware heterogeneity. This is true of both public cloud deployments, but also private cluster deployments. So you can have various GPU generations, A100, B100, P100, K80 that you accumulated over time. You can also have other architectures completely, like the TPU, FPGAs, and so on. It turns out this heterogeneity makes resource allocation quite a bit more challenging, partly because the models and the operators that are commonly used today perform quite differently across these hardware architectures. So here I'm showing normalized throughput with respect to a K80 GPU on a V100 GPU for a couple of different models. And you can immediately see that these different models experience quite different speedups when moving from the slower K80 GPU to the faster V100 GPU. It turns out that these varied speedups have quite interesting implications on how we should allocate resources. So a common scheduling policy could be round-robin scheduling, where you give different jobs equal times on the different types of resources that you have. But you can actually see that this can lead to quite unfair consequences. For example, if we were to give the ResNet 50 and transformer job equal time on the V100 and K80 GPUs, we see that the ResNet 50 job would be treated quite unfairly in this case, simply because it sees such a large slowdown when moved on to the K80 GPU. So our goal here is to provide heterogeneity-aware scheduling, and heterogeneity not only comes about from the models and the hardware that we're using, but also from the objectives that we might want to optimize across this cluster. So possible objectives could include single job objectives, like minimize the total cost of training of a single job. But you could also have multi-job objectives, such as fairness or even hierarchical policies. It turns out that optimizing for these multi-job objectives is quite a bit more difficult, because we need to consider interactions between different jobs on this shared pool of resources. Turns out that we're not by any means the first cluster scheduler designed for deep learning. But it turns out that a lot of these existing cluster schedulers do not consider performance heterogeneity. They were designed explicitly for homogeneous clusters where we have a GPU of a single type, for example. There are more recent schedulers like Allox and Gandiva Fair that do consider performance heterogeneity, but they only consider they only support specific objectives. And so supporting other objectives would require complete scheduler redesigns. And so in this work, we tried to come up with a scheduler that is able to express a number of different policies as optimization problems over an allocation. And then using a policy agnostic ground-based scheduling mechanism, we can actually realize these allocations for various objectives using the same scheduler software. And it turns out that we're able to improve objectives such as average job completion time by up to 3.5x using the exact same set of resources. So we want to support a large number of scheduling policies and make them heterogeneity aware. These include simpler policies like FIFO or shortest job first, more complex fairness policies such as those seen in recent work, and even hierarchical policies such as a multi-level fairness policy. Our main insight is that policy objectives can be expressed as functions of throughput. So for example, in a shortest job first policy, the duration of a job is just going to be the ratio of the number of training iterations that the job needs to run divided by the throughput. The cost of a job is just going to be the duration times the per unit time cost of various resources. And the speed up of a job is just the throughput of the job divided by some reference throughput. However, what's not immediately clear is how we should actually think about throughput in a heterogeneous setting, especially one where jobs can be moved between resources of different types during its duration. And so what we did here in Gavel is we found that we could express allocations as the fraction of time a job should spend on each type of accelerator. For example, an allocation could specify that job 0 should spend 60% of its duration on a V100 GPU and 40% of its duration on a P100 GPU. Similarly, job 1 could spend 20% of its time on a V100 GPU and 60% of its time on a P100 GPU. One thing I want to note here is that these allocations are intended to be valid only between specific boundaries, and we would recompute allocations either at periodic intervals of time or when what we call a reset event happens. So you could think of this as a new job arriving at the cluster or an old job completing. Another thing to note here is that the optimal value of this allocation matrix is very much dependent on the choice of policy and objective that we want to optimize across the cluster. Next natural question might be, how do these allocations actually affect job throughputs? So this is the same allocation as what I showed on the previous slide, just shown visually. And so let's assume that job 0 has a throughput of 100 iterations per second on a V100 GPU and 40 iterations per second on a P100 GPU. Then we can see that its throughput in net, given this allocation, if this allocation is realized ideally, would be 60% times 100 plus 40% times 40, which works out to 76 iterations per second. Thus, we see that by time averaging the individual throughputs that jobs observe on the provided resource mix, we can obtain the job's effective throughput. Mathematically, this is pretty easy to compute. It's just going to be the dot product between the raw throughputs for this particular job and its allocation. And so effective throughput allows us to easily capture the effect of moving a job from a faster to a slower resource type by explicitly incorporating this matrix of raw throughputs, which is T sub m here. So now let's consider how we can actually use this framework to make existing policies heterogeneity aware. And so let's consider a fair sharing policy where we're trying to equalize the resource share that each job receives on various compute resources. You can think of this as solving a maximum fairness problem. In the homogeneous setting, this is just computing a maximum allocation subject to some constraints. So these constraints are just ensuring that the allocation we compute is valid. And one easy way to make this heterogeneity aware is to just slightly change the objective. And so now instead of computing a maximum allocation directly over the allocation, we can instead compute, we can instead make our objective the max min of some normalized effective throughput. Note here that we add this normalizing term in the denominator to make sure that we can actually compare throughputs across different types of jobs, right? So for example, a ResNet 50 job could maybe train on the order of hundreds of iterations per second, while a language model might only be able to train at the rate of tens of iterations per second. And so in order to make sure that we can actually compare across these two types of jobs, we introduce this normalizing term. And it turns out that we can incorporate other objectives as well, similarly, and we can make them heterogeneity aware as well.
Hi, Deepak, I have a question.
Yeah.
Can you go back to the previous slide?
Yeah, sure.
The one with figure?
Yeah.
Okay, yes, this one. I can imagine that you have constrained that all of the jobs occupy of the resources, but what if they cannot be perfectly fit into the one you showed? Say there are bubbles between the jobs on these devices.
Mm-hmm. Yeah. So here, yeah. So there could be idle periods as well, where, for example, there's nothing running on a particular job, and that would be the case where, for example, the cluster is undersubscribed. But essentially, the way we actually schedule jobs onto resources is using a RoundBased Scheduler. And so essentially, when jobs are added to the cluster, we do not immediately give them resources. We actually wait till the next round
I see. Yeah.
until we give them resources. And so what that actually means is that you can think of us scheduling a snapshot of jobs that are active on the cluster at any point in time. And since we actually give resources in rounds, we can ensure that if there are enough jobs to fill the cluster, we can ensure that every resource in the cluster has some job running on it.
Yeah, I can imagine you would not like to context switch frequently.
Yeah, exactly. That's a great point. And in our paper, we actually show the effect of the round duration on, which is essentially, you can think of it as the frequency with which you context switch on actual performance. Yeah.
Okay, thank you.
So I don't have much time left, but let me quickly show a snapshot of results. And so these were results run on a simulated cluster with 108 GPUs of different types. We evaluate each policy on multiple different traces. Each trace has a different Poisson arrival rate. And so you can think of it as having different average input job rate. And so we evaluate three policies here. One is the vanilla max-min fairness policy that I talked about a couple of slides ago. This is the blue curve, the least attained service policy. And then I also showed two heterogeneity aware versions, which is this orange line and this green line. So the green line is Gavel with space sharing, which is essentially Gavel's heterogeneity aware policy, but also with this additional performance optimization called space sharing. And there are a couple of interesting results here. The first is that on the same set of resources, Gavel's heterogeneity aware policies are able to sustain higher input job rate just by doing a better job of mapping training jobs to resources on which they have high affinity, and doing this in a multi-job aware way. We also see that for a given input job rate, we're able to improve metrics like average job completion time by as much as 3.5x. And we can also look at the CDF for job completion times, and we see that we're able to shorten the tail of the distribution as well. And so quick takeaways here. So we see that performance heterogeneity can make resource allocation much harder, and differing choice to users can still lead to bad outcomes. But instead, if you're able to formulate policies as optimization problems, we're able to use these heterogeneous resources much more efficiently. While all of this sounds really promising, I believe we're really only at the tip of the iceberg when it comes to system support for machine learning and inference. I think there are a number of different exciting directions for future exploration. And I am looking for interns for this summer. So if any of this sounds interesting to you, please do reach out. And with that, I'm happy to take questions.
Thank you, Deepak. I have a question. I'm wondering, this is a pretty basic question. I'm not much of a systems person. Yeah. So we were talking about doing scheduling at the granularity of jobs. I'm wondering if anybody does work at in scheduling at the granularity of operators within jobs. So view a job as a set of operators and kind of handle it on an operator by operator basis.
Yeah, I think people do look at that. I mean, I think the distributed model training stuff that I talked about in the first half of this talk is kind of one such problem where you are trying to determine where to place individual operators in the model on different devices, and also how do you schedule computation given those placements. But yeah, like, I mean, that's just one flavor of problem there. There are other people who look at like compiler techniques and how do you kind of co-optimize these different operators. Can you reduce the number of memory accesses and so on. But yeah, like you can definitely think of scheduling at a macro granularity, which was the second half of this talk, and scheduling also at a more micro level, which was the kind of first half of this talk.
Yeah. Awesome. Thank you.
May I ask a question? Is anyone else asking a question? Okay, I'll go ahead then. First of all, thank you very much for this talk. I have not worked on distributed training, but I think this presentation has made it a lot more approachable for me. So I really thank you for the clear discussion. I have a question though, something that is related to what I've worked on.
Yeah.
So you talked about heterogeneous systems where you have different accelerators available, and most of the examples were quite reasonably GPUs.
Yeah.
Right. And I imagine you're going to be operating on floating point data.
Yeah.
Have you considered settings where the data types could vary, which could affect the application level results? Is this a problem you have considered or are considering?
Yeah, great question. So yeah, like a lot of everything we considered in this work was without playing with semantics. But I think you can absolutely try to incorporate approximations into this scheduling formulation. So one way to kind of think about this is sure, you could like play with floating point format. I think the specific policies that I showed only talk about throughput and think of you like if you're not playing with semantics, you can think of throughput as a reasonable proxy for time to accuracy, right? Which is really what people care about, right? Like the total amount of time needed to train a model to a desired accuracy level. But if you do start playing with semantics, throughput is no longer a good proxy for time to accuracy, right? And so you'll need to kind of do something a little more clever. It's not something I'm actively thinking about, but I do think it's like a really interesting area of future work for sure.
Certainly. Well, thank you for that.
Yeah.
Hi, Deepak. Another question for me. I think the model you mentioned are mostly variants of transformers, say language models, something like that. I wonder how difficult it is to, apply the parallelizations you mentioned to any deep learning models.
Yeah. So great question. Yeah, I think like our SOSP paper from a couple of years ago on pipe dream actually considers non-transformer models. So we looked at basically how to parallelize things like image classification models. Yeah, I think it's definitely a reasonable problem. I think the most generic problem statement for something like this is, given some arbitrary model architecture, how do you determine how to compose some of these existing parallelization primitives to optimize throughput? And definitely we saw in our results that pipeline parallelism, for example, can be a viable alternative to something like data parallelism, even for open source as part of like the Megatron system, only works for transformer models. But yeah, definitely pipeline parallelism can be used for other types of models as well. Yeah.
Cool. Yeah, I also wondering, up to now, is network the bottleneck or the computation the bottleneck for distributed training?
Yeah, it very much depends on the model and the hardware you're using. There are certain settings where when communication is the bottleneck. For example, these transformer models have quite large weight representations, and so they're quite expensive to distribute. And if you have slower interconnects between different servers, then you are going to be communication bound. But there are other models like ResNet that are a lot more compact, which actually scale quite well, even on slower interconnects. And so ResNet 50 would be an example of a model that's more compute bound, even in the distributed setting. Yeah, but it all really depends. There's no like one size fits all answer. Yeah.
Yeah, I think so. Yeah. Any other questions? Okay, thank Deepak again for the great introduction to pipeline parallelism and his scheduling works. Nice talk. And I think Deepak also say you're welcome to apply for interns at his group.
Yeah. I mean, I think interns are one way of collaborating, but don't have to be the only way, especially since I'm just across the pond. So yeah, do reach out if you find any of this interesting, and we can set up time to chat.
Feel free to send this to those who are interested.
Yep.
Thank you very much.
Thank you so much, Deepak. That was awesome.
Cool. All right. Thanks a lot.
Thank you.
Thanks.